Good evening, ladies and gentlemen. Good evening, or welcome to the last BrisScience of 2016. If this is your first, thank you so much for coming along tonight. We are a series of free public lectures on science held once a month at the fabulous Edge Theatre at the State Library of Queensland. They're brought to you by the University of Queensland, where we aim to bring not just the best scientists, but also the best communicators to speak in Brisbane, and tonight is no exception. We'll get into our speaker shortly, but just a couple of bits of housekeeping first. If you have a mobile phone, now would be a great time to turn it to silent. However, feel free to keep Twitter available because we will be live tweeting throughout the evening, and you can ask questions of our speaker tonight over Twitter using the hashtag BrisScience. Alternatively, you might have received a question page on your way in, and you can write down your question there, and at the end of the talk, we will go around and collect as many of those as we can, or collect all of them, and we will ask as many as we can before the night is over. Afterwards, we'll be having some food and drink outside, and you're more than welcome to join us for any further questions or discussion that you might have. I think that's all of the housekeeping. So tonight, it's my very great pleasure to be introducing David Reitze. David is the Executive Director of the LIGO Laboratory at the California Institute of Technology and also Professor of Physics at the University of Florida. His, among many claims to fame, is he's a member of the LIGO Scientific Collaboration that was awarded a 2016 Special Breakthrough Prize in Fundamental Physics for the discovery, for the first time, 100 years after they were predicted by Einstein, of gravity waves. And we are incredibly lucky to have him here in Brisbane tonight to speak to our wonderful BrisScience audience about that discovery. So please join me in welcoming Professor David Reitze.
I'm very delighted to be with you tonight. I'm here actually attending a scientific conference, the Australian Institute of Physics Scientific Conference, and I was invited to give a lecture, and it's always a great opportunity. I love talking to people about gravitational waves because I think it's really interesting, and I love that so many people are here to listen. So let me get started. This is a story that actually begins about 1.3 billion years ago. All right, when these two black holes were orbiting around one another, and as they orbit around one another, the orbital dynamics, the emission of gravitational waves, and I'm going to go into all this in a little more detail in the talk, led them to collide with one another and produce a bigger, more massive black hole. All right, we're going to skip through most of that 1.3 billion years, and we're going to go to about 100 years ago, when Albert Einstein came up with a theory of gravity called the general theory of relativity. It was an extension of the special theory of relativity, where he predicted that gravity had a very unique mathematical character and that it would explain the way objects move in a very different way. And this is a photocopy of the paper. That equation at the bottom is a very famous equation that people who do general relativity still use today. That g mu nu is something called the metric tensor. It's the way we measure distances in space-time. All right. Now we know special relativity. Special relativity, everybody is familiar with the equation E equals mc squared. It's probably the equation that's most known in the world. And it's actually worth thinking about what this equation means, because I'm going to come back to it later on. E is energy, of course. M is mass. And it says that energy is equal to mass. All right, so matter and energy are the same thing, and one can be converted to the other. And you do that with this conversion factor of c squared. Now, c is the speed of light, another very important constant in physics. It's the ultimate speed limit of the universe, at least as far as we know now. And it's a very big number. It's 3 times 10 to the 8th meters per second. So that says that a little bit of mass turns into a lot of energy, because 3 times 10 to the 8th squared is a big number. Okay, but now let me talk about general relativity. The equation is much more complicated. If you know something about tensor mathematics, you'll recognize this. If not, you don't actually need to know anything about tensor mathematics, because I can explain it in words. All right, first of all, this side is space and time. And in special relativity, Einstein said that space and time are equal. All right, if objects that are moving at a very fast velocity, at any velocity, have different coordinates for space and time. To really see it, you have to go fast. On this side is matter and energy. So that's the M and the E that I talked about before. And then there's this constant here, 8 pi g. And I should point out, historically, this is a mathematically very bad equation because that g is not the same as that g. Nevertheless, physicists use that notation. That's okay. What does it really say? What it says is that space and time are now equal to matter and energy with a constant. All right? And the constant is a very tiny number. If you calculate that constant, it's about 10 to the minus 43, which is a very, very tiny number. Now, think about what Einstein did here, because it's important. First of all, when Einstein started thinking about the fundamental nature of the physical world, we had 4 quantities: space, time, matter, and energy. Einstein then said, in special relativity, matter and energy are equal, and space and time are equal. In general relativity, he said they're all equal. All right? So this basically unifies space, time, matter, and energy. All right? But there's a trick here, and it's why this experiment is so hard. It's why it took 100 years from the time that Einstein predicted gravitational waves till we were able to detect them. And that's because that constant is so tiny. It says that you need a huge, huge, huge amount of matter and energy to make a little bit of change in space-time. Let me make that a little more realistic to you in this diagram. So this is a picture of the Earth orbiting around the sun. Everybody understands that. Before Einstein, the explanation for why the Earth orbits around the sun was that there was this force called gravity, and you could write down the mathematical expression for that force. It's proportional to one mass, it's proportional to the other mass, and it's inversely proportional to the distance squared between those two objects. And then there was this funky gravitational constant, big G, that I showed you earlier. All right, and the Earth orbited around the sun because there was a force. The Earth has orbital angular momentum and energy, so it's moving, but it's bound to the sun because of this gravitational attraction. All right, what Einstein did was answer a question that Newton never could, and he knew it was a problem. All right, nowhere in Newton's theory of gravity does this fundamental speed limit come in, the speed of light. All right, Newton's gravity is instantaneous, which means two objects that are separated by very large distances essentially know each other are there because they communicate instantaneously. This violates special relativity and general relativity, so Einstein came up with a theory that explained how that information gets communicated. And it gets communicated through geometry. So this grid that you see here is basically space-time. Now, I can't show you 4 dimensions, 3 space and 1 time, so I'm just showing you as 2 dimensions here. But you'll see that where the mass of the sun is that the normal geometry that you and I think of, you know, X, Y, and Z geometry, is no longer valid, because what's happening is this massive object, the sun, is warping, curving, bending the space. It's changing the geometry of space, as is the Earth over here, but you see, because it's much less massive, it's just making a little dimple in space-time. All right, and why is the Earth now moving around the sun? Well, the Earth has energy, it's got orbital energy, but it's following its natural geometry, and its natural geometry in this picture that I draw here is not a straight line. It's a curve. It follows a curve around the sun. And if the sun were to disappear, if it were to instantaneously poof out, all right, the Earth would not know that for another 8 minutes, because that's how long it would take. That's the speed of light between the Earth and the sun, and that's how long it would take for this geometry to relax back and the Earth to realize, oh, I'm no longer gravitationally bound. All right, so that's sort of a 1, 2, 3 slide primer in general relativity. So where do the waves come in? All right, where are waves in this picture? And I'll show you where the waves are. All right, the waves come when you have objects that are accelerating. All right, they actually radiate energy in the form of gravitational waves. All right, this is a nice movie. These are an artist's rendition of the 2 black holes that LIGO saw on September 15th of last year. And you see the geometry there. And let me now start the movie. You see these black holes are orbiting around one another. And as they're orbiting around one another, they're emitting gravitational waves because they're in acceleration. When you're in an orbital motion, you're accelerating. And eventually they radiate energy, so much energy in gravitational waves, they collide, come together, and this big burst of gravitational energy goes out the door. All right? And then you detect it 1.3 billion years later. All right? That picture is nice to sort of conceptually explain how a gravitational wave works, but it's not how you actually measure a gravitational wave. So if you're an experimentalist like I am, you say, okay, what do I really want to measure if I'm measuring a gravitational wave? And what you're trying to measure is a change in length per unit length. So the amplitude of those waves that I showed you in the last movie is a change in length per unit length. And this is a very important equation. All right? In physics, this quantity is called a strain. If you've taken physics, you might remember it. If I have an aluminum bar and I put some pressure on the aluminum bar will shrink a little bit because you're basically straining the bar. Of course, it takes a lot of energy to make that shrinkage. And the amount of shrinkage is proportional to the length. The bigger the length, the more the shrinkage. Right? Well, that's what gravitational waves are. But the way they interact with space-time is not like what I showed you in that other movie. Basically, you have to think about it as a differential strain. So I'm going to play another little movie here where gravitational waves are coming at you. Here they come. All right, so these are two gravitational waves, and you could think of these as coordinate systems, all right? So there's an XY coordinate system here. On one cycle, the gravitational wave is stretching one dimension and it's compressing the other dimension. And then as you go through that, that cycle repeats. And there are two different flavors. We call them polarizations. Just like light is polarized, so is gravitational waves. So what you would be measuring as a gravitational wave is coming at you, you would stretch a little bit this way, you'd compress a little bit this way, and then you'd stretch a little bit this way and compress a little bit this way. And you might think, okay, that sounds like a pretty easy thing to measure. You'd be wrong. And the reason you'd be wrong is that the effect is very tiny. So this is another slide or another screenshot of Einstein's paper where he predicted gravitational waves. And this quantity A is that delta L over L that I just told you about. It's the amplitude of the gravitational waves. All right, I don't read German, but I can go on Google Translation, and so I did that. And what this paper says is that then A must have a virtually vanishing value in all imaginable cases. So what Albert Einstein is telling us with that sentence is don't bother looking for gravitational waves because you will never find them. All right? For the reasons that I told you earlier, that the effect, the size of those gravitational waves is so tiny because you need a lot of mass to be able to change gravity. So you need a lot of accelerating mass to be able to produce measurable gravitational waves. And when Einstein did the calculations and he understood the technology of his day, he said, forget about it. Just go home and do something else. All right? And he was right. I mean, he was absolutely right. But this was 1916. So fast forward 100 years, and we've gotten to the point where we can measure those waves. So let me tell you now, let me give you a sense of scale about these gravitational waves. So suppose you wanted to create one in your laboratory. This guy's a mad scientist. He says, I'm going to produce a gravitational wave. All right, the way he's going to produce a gravitational wave is he's going to put two big massive objects, 1,000 kilograms apiece. He's going to separate them by about a meter, and he's going to spin them around 1,000 times a second. All right, this dumbbell that he's producing turns out to be a very, very efficient emitter of gravitational waves, even though those gravitational waves are very weak. All right, so you can calculate, all right, from Einstein's theory, how much strain, what the amplitude of the gravitational wave is that you're seeing here, and the answer is that. Okay. So you can count the number of zeros, all right, and then you'll get to the one. I'll save you the counting. There are 35 zeros before you get to the one. So that means you're looking for a change of 1 part in 10 to the minus 36. All right, any experimentalist worth his or her salt would just say, we're done, go home. So you don't do this experiment. But you can do this experiment in nature, and this is why gravitational waves are so fundamentally exciting. Turns out nature does this experiment, not all the time, but frequently enough that we will be able to detect it going forward. These are 2 neutron stars. Now, it's the same experiment that I just showed you. Now, instead of having 1,000 kilograms, you have about 1 solar mass, about 1.5 solar masses. You have 2 of them that are locked in an orbit, and they're spinning around. And actually, realistically, when these guys are very close to one another, they're actually spinning around at about 1,000 times a second. All right? They're moving very rapidly, significant fractions of the speed of light. All right? So you've got massive objects with a lot of energy that are close to one another, that are radiating gravitational waves, you can do the same calculation. Well, okay, it's a little better. All right, it's 10 to the minus 21. All right, so it's 20 zeros and then the 1. That is still a daunting number for an experimentalist to be able to measure. All right, but I come back to the delta L over L because how to design a gravitational wave detector is really encoded in this equation. All right, it says if I make my L long enough, all right, I don't have to measure such a small delta L. So if I were to make a gravitational wave interferometer, which we'll get to in a minute, that was a meter long, it would say that I would have to measure to a precision of 10 to the minus 21 meters. All right, that is a very tiny number. But if I can make my gravitational wave detector a kilometer long, all right, well, now I've gained a factor of 1,000, so I only have to make my sensitive displacement measurement, that's the delta L here, oops, that's the delta L, to 10 to the minus 18 meters, which is still an awful small number. And the first time that many physicists, myself included, heard about this idea of measuring gravitational waves using interferometry to this level of precision, the reaction is, it can't be done, you're crazy. And then you start to understand how you make precision measurements, and I'm going to walk through a little bit of the challenge in the next couple of slides here. You realize it's not crazy, it's really difficult, but it's not crazy, it can be done. All right, so let me now talk about LIGO, the detector, because I've given you the background here. General relativity, gravitational waves, you need big massive objects that are really astrophysical in nature to be able to see them. So how do you make a detector that detects them? All right, let me start with where I am. I'm at Caltech, as Joel noted. I work with a group of very talented engineers and scientists, about 190 of us. We are located at Caltech and MIT. Our observatories, there are 2 of them. One is in Hanford, Washington. The other, and that's in the northwestern corner of the United States. The other is in Louisiana. If you've ever been to New Orleans, Louisiana, you weren't that far from our interferometer, right? And as Joel also said, I work with a much larger group of scientists, about 1,000 scientists that make up the LIGO Scientific Collaboration, including many scientists from universities in Australia. And you might ask, why do you need 1,000 scientists to do this? And as I go through it, you'll see the scale of the science that we're trying to do. You'll understand that it really does take a huge number of people to be able to do all the things you need to do to make it together. And I'll point out, by the way, it's not just scientists. We have a lot of engineers, and those engineers have been extremely important in designing equipment for us to be able to do it. So, and I must point out that we get our funding from the National Science Foundation, which has supported this project for 40 years. When LIGO was first proposed, it was very controversial because of everything I just said. How can it work? What kinds of sources are you going to see? The National Science Foundation for the last 40 years has backed us, and that's been very beneficial. Okay, so here is one LIGO detector. This is the one in Livingston, Louisiana. All right, remember I said the L, the baseline over which you make the measurement, has to be long? Well, our arms are 4 kilometers long. You might ask, why 4? Why not 8? Why not 1 kilometer? That turns out to be more of a money question than a science question. All right, if somebody had given enough money to build an 8 kilometer or 10 kilometer or 12 kilometer, we probably would have, but the NSF said we only have this much money, so we built one of those. And just to give you a sense of scale, those are automobiles down there. All right, so you get a sense here. Here's another one. It's identical. It's an absolute clone of the one I just showed you in Livingston. This one is 3,000 kilometers away in Hanford, Washington. And I'm not going to tell you, but I'll suggest something to think about. You might ask, why do you need 2 detectors? Why not just 1 detector? Because obviously it's almost twice as expensive to build 2 as it was, and there's a really important reason for that. Okay. Now, I showed you this stretching and compressing of space-time, the strain that we're trying to measure. How do you measure it? Well, there are a number of different methods that have been proposed. The one that works is something called interferometry, all right, which is basically a way of using light to make very precise distance measurements or changes in the distance measurements. So this is how we get the delta L, all right. Here we have a laser. This is a movie that I'm going to show you, so you'll get a sense of how this works. Here we have a laser. So this is a very ultra-pure stabilized laser. This is something we call a beam splitter. It's basically a half-silvered mirror. Half the light gets through and goes here. So this is 4 kilometers away. Half the light reflects and goes here. That's also 4 kilometers away. And then there's something here called, it's a photodiode. In the movie, it's a screen. So what I'm going to show you is the principle of interferometry. And the reason this works and works so well is because the best ruler that you can possibly come up with in nature is the wavelength of light. All right? We can measure the wavelength of light, and we can measure fractions of the changes in wavelength of light. That's what interferometry does very, very well. All right, so I'll start the movie. And the laser's going to come out. You're going to see a ribbon, a red ribbon, but you'll see 2 waves on that, and those waves are color-coded yellow and blue. And they'll reflect off, they'll come back. And if we configure the distances between the beam splitter and the mirrors right, they come back such that no light gets to this detector here. So all of the light interferes and destructively. But when I see these small changes, all right, basically what will happen is it'll break that interference pattern, and you'll start to see light appear on the screen here. Or in this case, it goes into a photodiode, which turns into electrons, photocurrent for us. All right. So this is the whole principle behind gravitational waves. All right. In our case, the wavelength of the light that we use is 1 micron, or 10 to the minus 6 meters, all right, which is a heck of a lot bigger than that 10 to the minus 18 meters that I told you. So in fact, this diagram even still exaggerates the amount of sensitivity that we need to make this detection. So we have to measure a change that's better than 1 trillion times that, okay? In other words, less than 1 trillionth of that is what we measure with LIGO. How do we do it? Well, the way we do it is we understand all of the noise sources, or all of the things that can possibly pollute or corrupt the measurement. All right, so here's, again, the picture of the, this is exactly the same picture I showed you before, now just looking from the top. And I want to walk through all the ways that nature or humans can conspire to mess this experiment up. The first one is seismic noise. All right, we live on the Earth. Our interferometer's on the Earth. All right, here in Brisbane, you're close to the Pacific Ocean, and right now the ground is moving below you at about a micron, all right, about the same way as the wavelength of light in amplitude. You don't feel it because it's very tiny compared to what we can sense, but compared to what LIGO is trying to do, 10 to the minus 18 meters, that's an awful lot of motion, all right? And so we have to basically attenuate the seismic motion, all right, in our interferometers such that the mirrors do not feel it to a level of about 1 trillion. Another thing that's more technical than fundamental is our laser. Our laser, as I said, is one of the most stabilized. I think it is the most stable laser in the world. When you think about lasers, you think they're very pure light. So if I point that up there, you see there's green light. It's perfectly monochromatic. It turns out it's not, all right? And you have to go to great troubles to stabilize the wavelength, or frequency alternatively, and the amplitude. So we go to great pains to put feedback loops into our system to be able to stabilize the laser. If the laser wavelength were to change, if you walk through the interferometry argument I gave you before, you would find that that would lead to a spurious signal. It would look like a gravitational wave detector. Okay, what else do we have to deal with? This is a fun one of my favorite ones. Quantum noise or shot noise. What is quantum noise? Well, it comes in 2 flavors. Light turns out to be a quantum mechanical object. In other words, photons are discrete, all right? Even though the light that hits you, your eyes are sensing them continuously, light really comes in packets, and the arrival time of the photons is random, and it has to do with the number of photons that are being delivered in a given time. All right? That is something called shot noise. So even if I had a perfect laser, all right, and everything else were perfect, there would still be some randomness in the time of arrival of light going from here to here and going from here to here. And that randomness would lead to a change in the interference pattern. So every once in a while, in fact, all the time, I would still see a little bit of light, and that light would be fluctuating on this photodiode here, just because of the fundamental nature of light, the randomness of light. This is a manifestation of the Heisenberg uncertainty principle, all right, that any object that is quantized, all right, you can't know its momentum and its position or its energy and its time at the same time. So that's what we're up against here. We're up against quantum mechanics, which is hard to beat, all right, but not impossible. Then you have radiation pressure. Now this is a very interesting one because I can beat shot noise by turning up my laser power. The more laser power I have, the more photons that I put in my system, the more the average number of photons overrides the randomness. The signal to noise in our experiment goes as the square root of the power. All right, so I can win by going to high powers. All right, but then you pay a price, and the price you pay is that photons carry momentum. All right, so light, because it's a particle, it has energy. When it hits an object and reflects off the object, it imparts a tiny bit of momentum to that object. All right, in this case, we have lots of photons because we've turned up our laser power, all right, and those photons are hitting the mirror, and so they're pushing the mirror back and forth. And of course, that's happening here and also here. So the mirrors are getting buffeted, if you will, by this, continuous onslaught of random arriving photons. All right, that's a problem. And it turns out the right way to solve that problem is to turn down your laser power. So where do you go? Turns out there's a happy medium, and it's something called the standard quantum limit, where if you tell me what the wavelength of the light is and what mass, how heavy you make these mirrors, I will tell you what the right laser power is. I'll also point out that you can even do better than this. You can even beat this quantum noise with something called squeezing. It turns out we can trick Heisenberg. We can trick the uncertainty principle into thinking that at one point in the measurement, the amplitude, in other words, the amount of buffeting of the light on the test masses is very small. And at another time, that the arrival time of the photons here is very small. It's called and it's optical squeezing or quantum squeezing. And it's something that we don't do now, but we will do it later. Anyway, let me keep going. There's another fundamental problem. This is a pernicious one. All right, it's basically that every object that's at a finite temperature, all right, has energy stored in it. This is something called statistical mechanics. And in our case, the energy is stored in the mirrors. The mirrors are at room temperature, all right, and the surface of the mirror is actually moving, all right, and it's moving about 10 to the minus 20 meters, it turns out. Right? And so that doesn't sound like much if you're trying to measure 10 to the minus 18 meters, but it turns out that a lot of things that you do to the mirror can make that much, much worse. So we have to be very selective in what kind of materials we use, what kind of coatings, optical coatings we use, to be able to get rid of this noise. And if you paid attention, you say, oh, well, the other thing you can do is turn down the temperature. And the answer is yes. That's, in fact, something that will happen in the next generation of gravitational wave detectors. But for now, we're operating at room temperature. Okay. And then residual gas scattering. So the fact that we live in an atmosphere, you can see through the atmosphere, this laser beam can go through the atmosphere, but unfortunately it scatters, and if it scatters, it leads to noise. Basically, molecules will change the phase or delay the light in a random way, and that will compromise the measurement. So that means the whole interferometer has to be in a big vacuum system, all right? And that's not terribly complicated, but it adds some expense. All right, so let me walk through some of the ways that we deal with this, all of these noise problems. This is a picture of a piece of fused silica that will become one of the mirrors in our interferometer, the test mass mirrors. It is ultra pure. It's the same kind of fused silica that when you make a phone call and your voice gets turned into light pulse and fiber optics, that's what we buy here. It's very expensive. We then suspend these mirrors. Now this is hard to see here, but here's the mirror. This is what happens. This becomes this at the end of the day. And it gets hung from another object here, and then it gets hung from two more objects. So we use something called harmonic principle of harmonic oscillation to isolate the vibration. And remember I said seismic noise is bad, so above here is basically a really sophisticated seismic isolation system. The analogy that I would give is if you drive a high-end automobile like a BMW or a Mercedes-Benz, when you drive over a bumpy road, you don't feel the bumps because there's a shock absorber, and there are shock absorbers that read out, and sensors that read out the way the ground is bumpy, and then feeds back to the shock absorbers to cancel out that motion and keep the platform of the car and your seat smooth. We do that, but we do it about 1,000 times better than Mercedes-Benz does it. And it's very expensive, so. Okay, and here is actually quite interesting. Let me go back here for a second. Oops, sorry. This is, these are two scientists that are actually welding fibers onto those mirrors. So the only contact that these mirrors have with the rest of the world is through 4 fibers, very tiny 400 micron diameter fibers. And the reason for that is because we need to suspend them from this suspension. And to do that is a very, very technical and complicated process that took a lot of time to work out, but we were able to do it. Okay, here's a picture of the whole smash. So this is the corner station. So that's one of the inside of one of the buildings I showed you before. So the laser would be over here. The beam splitter would be here. There are other mirrors in this system, and there's lots of other optics in this system. So you get a sense of scale of how complicated this is. Here's the laser, which is, as I said, down the end here. And our laser, because it's powerful, it's about 180 watts, and because it's ultra stable and ultra clean, we have to work in a clean room. So it's not quite as clean as, say, a semiconductor fabrication plant, but it's maybe 1 or 2 levels above that. Okay, you put that. Oh, here's just one more picture. This is. I like to show this picture because this is the only laser that you can actually see. The 1 micron light is invisible, so you can never see it. But we use green lasers to stabilize some of our optical cavities, and you can see that here. Okay. Oh, the vacuum system. I have to brag about our vacuum system. All right. Basically, what we do is we cut a hole in the atmosphere that goes 4 kilometers. And we do that by putting in a volume of about 10,000 cubic meters, 9,000 cubic meters, 30,000 meters squared of surface area, 50,000 meters, 50 kilometers of spiral welds. You can't just go out and buy these tubes, you have to make them. And we make them by taking sheet, basically steel, rolling the steel up and welding it together. So there's 50 kilometers of welds, which means there's 50 kilometers of places where you could have a leak, all right, in this system. And the atmosphere that we get is about I guess that's about 1/10 trillionth of atmospheric pressure. So it's quite low. It's not super high, ultra high vacuum, but it's very high vacuum. And of course, we have to do this 2 times. And I can tell you that we do have leaks in these systems occasionally, and it takes a lot of time to find them, but eventually we do. Okay, let me talk a little bit about Australia's key contributions here. I want to point out that as again, there were a lot of people that made, and a lot of scientists that made powerful contributions. I'm not going to walk through any of the technical aspects of this, but I just want to show you what an important role universities in Australia played in this system. So our beam splitter and some of the auxiliary mirrors were coated by CSIRO up until very recently. CSIRO had one of the best optical coating companies in the world. The University of Adelaide came up with a very clever way of measuring our thermal deformations as we put laser power into the interferometer. The mirrors actually change their shape, and we have to measure that and correct for it. And at Adelaide, they developed something called a Hartmann sensor that allows us to do that. That's been deployed. At the University of Western Australia, they discovered they actually weren't the first group to discover it, but they found that there was a very complicated and bad physics problem that we had to solve. And that's when you put a lot of laser power in this cavity. We have optical cavities in our system, all right? That can actually lead to something, has an esoteric name of parametric instability, but basically it comes back to the radiation pressure. So the light in the cavity acts as drums, and what it does is it beats on the mirrors, and the mirrors start moving, all right? And then they start scattering light out. And this process is very, very, it feeds back on itself, and it can actually kill our interferometer. And we recognized this in the early 2000s, and it's taken us about 15 years to figure out how to solve it. And then I talked a little bit about the squeezing. You see that here. The group in Canberra at Australian National University has pioneered some ways of generating these squeezed states of light that we can inject into our interferometer. So Australia is really a big player in LIGO. All right, so now let me come to I think the fun part of this whole story. So when I was working in LIGO, I wasn't thinking that we would detect black holes. I was thinking that we would detect binary neutron stars. All right, but the first thing we saw, and literally as we turned on our detector, we saw these signals, and they are amazing signals. All right, and the reason they're amazing signals is because this is almost raw data. You can almost see this in the data. And those of us who had been in the field for a long time were deeply convinced that you would never be able to see something this good. That all the way you would detect the gravitational wave, you would have to rely on a lot of statistical massaging of your data. You'd have to bring hundreds of thousands of computers in to be able to tease the signal out. No, you can see it right here, and it's just amazing. This is the signal we saw at Hanford. This is the signal we saw at Livingston. And there's some interesting characteristics in here. The signal, you can see the frequency changes. It gets higher as you go, and then all of a sudden it just goes away. All right? And each one of the phases of these waves tell you something about the orbital dynamics of these two systems. All right, so what did we see? Oh, yeah, let me tell you, we measured, remember I said we need to measure at about 10 to the minus 18 meters? The amplitude of this wave, all right, that we measured was 4 times 10 to the minus 18 meters. So to put that in perspective, that's about 2 1,000ths the diameter of a proton. So that's the level of precision that LIGO operates at. Okay, all right, so what did we see? All right, we saw 2 black holes. Now I'm back to the 1.3 billion years ago. One of them about 36 solar masses, the other about 29 solar masses. The simulation I'm going to show you a movie of what we saw. And the movie is not an artist's rendition. This is actually taking that equation that I showed you earlier, the Einstein equation for general relativity, and solving it on a computer for this system. And we have scientists at Caltech and Cornell, actually these guys in particular, that did this. All right, so just to get a sense of scale for this, because it's really hard when you first hear it to get your head around how just amazing this is. This guy is about 210 kilometers in diameter, all right? And it has 36 times the mass of the sun packed into it, all right? So it's a very compact object. By the way, black holes are, many people think they're exotic, and they are at some level, but they're also very simple. In fact, they're probably some of the most simple physical objects in the world. They can only be, they're described by 2 quantities: their mass, how much mass they have, and how much they are spinning. In other words, how much they have, their event horizons are going around. What you see here, these black things are representations of the event horizon. In other words, you can't see further into the black hole because light, if it gets there, it can't get out. So beyond this event horizon, beyond that black blob, is for physics an iron curtain. We know that it's massive because it's represented by the curvature of the geometry around it. But there is no matter in it. This is pure space-time. So this process of making a black hole takes matter, completely de-identifies it, basically makes it go away and just turns it into infinite curvature. All right? All right, this guy's a little smaller. He's only 30 times the mass of the sun and a little smaller in diameter. And what you're seeing, the stars in the background are just there for your, I would say, reference frame. So as I start the movie, you're going to see the orbital dynamics that produce that wave I just showed you. All right, here they go. Now you see these guys, and you're looking at the orbit face on, which is about how we saw it actually. So the reason the stars are moving behind you is because the light from the stars is being bent as it travels around the black holes because of the nature of the geometry. Light travels on a straight line, but there's no straight lines near these black holes because of the bend in the geometry. You see they're speeding up, they're getting closer, wham, they come together, and you see that little vibration at the end. That little vibration at the end is a burst of gravitational waves that comes out right at the last moment, all right? And so what you witnessed here, or at least what the simulation showed, is basically the death of 2 black holes. They did this sort of final last tango. They come together and they produce a larger black hole. The mass of this black hole was 62 solar masses. Now, if you remember what I told you before, and you do the math, you will find out that there's 3 solar masses that are no longer there. And where did those 3 solar masses go? They went into the gravitational wave. So during this process, during this last few orbits, the amount of energy that was radiated away was equivalent to 3 solar masses by E equals mc squared. All right. Now, what's more impressive is how fast it happened, and I'll come back to that in a second. All right, so we've actually discovered 2 and possibly even 3 gravitational waves, and the reason I say possibly is because we're very conservative in this field. So one event wasn't really statistically significant, but we saw the event that I just showed you was this guy here, and then towards the end of the run, actually on Boxing Day, we discovered another black hole merger, and then in October, this is very likely a 3rd one, but we don't say that with high confidence. Okay, I'm going to play you what we heard, and then I'll explain what I mean by that. What you heard was the first 2 sounds I played was basically the waveform that was produced by this gravitational wave. Now, how can I play it? The reason I can play it is because the frequency of these waves that were produced are in the audio band. Your ear can hear them. All right. Now, these aren't acoustic waves in the traditional sense. Basically, what's happening during this process is the 2 black holes produce gravitational waves that travel 1.3 billion years, wiggle our mirrors, oops, I went too far, here, come back, wiggle our mirrors by this 4 times 10 to the 18 meters, all right? The interference pattern, they do that in such a way that the interference pattern has that funny characteristic to it, and so you can think of the interferometer as a transducer. It's kind of like a DVD player, all right? And we can record the signal and then play it back in sound. And that's actually quite interesting. So you'll often hear that we've opened a new window on the universe, but we're now hearing the universe. The analogy is not perfect, but I think it's pretty good. All right. And the other thing you heard is the characteristic of the chirp. So this is something we call a chirp, and it became very famous after our discovery. All right. After we made the discovery on February 11th, the world reacted with a lot more excitement than I think any of us expected. So let me just show you how we popped in popular culture. So this is a cartoon that showed up in the UK Guardian. It's actually a panel of a cartoon on February 12th. And I'll read it for you because I think it's just hilarious. Obviously, we can't see these waves. The only way we know they are real is by using another extremely sensitive device, which detects scientists having feelings of excitement. All right? And this guy is very excited about detecting a gravitational wave. This person is very excited about a cheese salad sandwich. Probably more fun is in that white there. Fun fact, scientists' emotional reactions are also the fraction of a width of a proton. I'm a scientist. I can tell you this is just not true. We were over the moon when this happened. So you can now buy gravitational wave fashions. All right, this is a company in San Francisco, and she took the waveforms and put them on a dress here. And actually, it supports STEM education, science, technology, engineering, and math. So this is quite nice. The dresses aren't cheap. I think they're $200. But I can tell you that a lot of the people that I work with have gone out and bought dresses like this. You see them now? And actually, you can also get a tie if you want. All right. If you've ever been to New York City, you know that it's one big advertising campaign. And if you go to the Metro, in March, after our announcement, it took a month for this to show up. Scientists found gravitational waves in outer space. If only it were that easy to find an apartment in New York City with a walk-in closet. I've worked on gravitational waves for 20 years. I can only imagine how hard it is to find an apartment in New York City. And then the last one I'll put up, I think you guys get this over here, but maybe not. I don't know if you know who this is. This is Sheldon Cooper. This result really touched, I think, touched a part of the popular culture. Well, let me go back. I want to start this one again. All right, now I'm going to play something that was synthesized or developed by a very clever postdoctoral fellow on September 14th, 2016, 1 year after the discovery. It's kind of cheesy, but it also emphasizes this point that there's a lot of information content, and you can use that information content to make art. And while this was one that was done by a postdoctoral scientist, there have already been, that I know of, at least 4 or 5 serious composers who have written pieces that have incorporated these chirps, these sounds that I just told you about. Okay. Let me close. I'm going to come to the end, and I'm going to talk about the future. Because the future, we made these discoveries, and people were amazed. We were amazed. But we realized that seeing 1 or 2 or 3 of these things is not really that exciting. What you want to do is see a lot more of them. And we want to do it the way astronomers do it. All right. So what we know about the universe, and this is really what's most exciting about gravitational waves, what we know about the universe comes from tools, scientific tools that are developed. So one that we're familiar with is telescopes. All right, when Galileo first turned his telescope to the sky about 400 years ago, he saw mountains on the moon. He saw the moons of Jupiter. He saw phases of Venus. All right, he learned something fundamental that for the last 400 years has advanced to the point where most of what we know about the extragalactic universe comes from optical astronomy or X-ray astronomy. Right, so it's a very powerful way to look at the universe. Similarly, you can go in the other direction to subatomics, and we've been making for the last, really, not quite 100 years, subatomic accelerators where we slam particles into one another, moving at highly relativistic speeds, and look at the products that come off of that. And from that, we learned about things like the Higgs boson, the nature of the subatomic world. Neutrinos, perhaps not quite as well known as other things like electrons and protons and light, but nevertheless very important. Supernova, for example, produce neutrinos. And there's a big detector in Japan, all right? And neutrinos tell us a lot about, they're a very dark particle. They're very hard to detect. They don't interact with anything. But they do give us valuable information. And then there's also cosmic rays, all right, which are basically high energy relativistic protons or things that come out of very cataclysmic explosions, all right, that you can detect the cosmic rays that are produced by them. All right. Gravitational waves, and by the way, this is really the tools that we have. Now, we also have lasers and microscopes and things like that, and they also are valuable. But in terms of understanding sort of the cosmic universe, all right, this is what we've got. Gravitational waves are completely different. So the idea that we can now detect these gravitational waves with some regularity, we're going to be looking at the universe in a whole new way. And every time you do that, you see something that you don't expect. All right, so let me give you an example of how much of a scientific impact we think our discovery had. All right, so this is a nice picture of an X-ray binary. Basically, the reason we know there are black holes in the universe is because usually by the black hole there's a partner star, all right, a standard star, that unfortunately gets close enough, or at least for itself, it gets close enough to the black hole that the black hole starts sucking matter off the star, right? And what happens is that matter accelerates, it goes into the star, and by the time it gets to the event horizon, that black spot in the center, it's moving highly relativistically, and it's producing copious quantities of X-rays, all right? And for the last 40 years, we've been knowing about black holes, learning about black holes from the X-ray studies of these binary systems. All right. So here, and this is a semi-complicated plot, this is solar mass. So this is basically the mass of black holes, all the black holes that we've ever seen or ever detected. All right. These are the ones in X-ray studies, and you can see there are about 20 of them. All right, and their masses go from about 5 to maybe 15 or 16 solar masses. The LIGO detection, all right, the first one is this one. All right, there are many things here that were never seen before. The first is that there were two black holes together. No one had ever observed two black holes together because you can only do it probably with gravitational waves. Second, they're manifestly much more massive than these guys here. So this is the first evidence that heavy stellar mass black holes exist. I mean, this guy's a monster. He's 62 solar masses. These other guys, this one is even bigger. All right. Now, the power of this is that it took 40 years of X-ray astronomy to find those 25 black holes. It took us 4 months to find 6 or maybe 9 more. All right. So in the future, LIGO, the way I put it sort of colloquially when I want to sort of tease my astronomy friends, is that we're going to own black hole physics probably going forward in the next few years. We're not going to completely own it. Now, in fairness, if you're an X-ray astronomer, the precision with which you can measure the masses of these is much better than these. But nevertheless, we're going to be seeing lots of these. And in fact, we expect when you get our detectors to design sensitivity that we'll be seeing one a day, maybe. All right, and now the power comes not so much from black holes. Let me move away from black holes. But let me come back to these neutron stars that I showed you an artist's conception of earlier. When neutron stars do the same dance of death that the black holes that we observe do, they are spectacular because unlike the black holes, which just go whoop, all right, these guys, because there's so much matter moving relativistically, these guys produce light across the electromagnetic spectrum, X-rays, gamma rays, radio waves. Right? And so and even we believe neutrinos, although it's not 100% confident yet. So if you can see an event like these neutron stars, all right, not just with gravitational wave detectors, but catch it in the act with X-ray telescopes, optical telescopes, radio telescopes, PEV neutrino detectors, you can actually construct a picture of the physics of that, the astrophysics that you can't get any other way. All right, and the way we do it is we use time of flight. So it turns out that interferometers are very poor localizers of gravitational waves. So those black holes that I showed you before, all right, you don't really get good positional information, but if you have more detectors, you do. All right? And you can then, if you can quickly detect a signal, all right, and you get localization information from the fact that you know the time difference, so you, in some sense, triangulate the black holes. You send that signal to your friends who operate telescopes, and you say, look over there. All right, well, over there is still a somewhat imprecise quantity. All right, so let me motivate what we're trying to do in the future here by giving you a picture of where this field is going to go in the next 10 years. In addition to the two LIGO detectors, which made the detection that I'm talking about tonight, there is another interferometer in Italy, which is under construction. We expect it to start operating soon after the new year. There's another detector actually very near the neutrino detector in Japan that will be operating in 2019 or 2020. And we're building a clone of the LIGO detector, same thing you saw in Livingston and Hanford. We're building an identical clone of it in India. And you might ask, why these places? And it turns out that the more detectors you have, the better the time resolution that you get between them, and where they are on the Earth, all right, improves your resolution. And let me just give you an example of that. All right, so this is a complicated picture, but this is a sphere, put yourself at the center of the sphere. You can see the Milky Way projected along the sphere, that arc there that sort of goes off to the right. And you can ask yourself, with the two interferometers that we had, just the two LIGO interferometers, how good can you detect the signal? And you can see that it's really kind of bad. All right, if you're an astronomer, you look at this and you go, why should I even look? That's horrible resolution for me. You can fit 2,500 moons in that position. If I just add one more detector, all right, you get much better. And here's when you add Virgo, all right, you get, some of the places are very good. If you bring in India, you get even better. So even four detectors makes those big splotches become very, very localized. And this is where astronomers are really excited about this, because we want to be able to do not just gravitational wave astronomy, but multi-messenger astronomy in the future. All right. And I should point out that the gravitational wave detectors that we use are not the only gravitational wave detectors. There are gravitational waves that have longer periods, lower frequencies, all right, that you can detect in space. There's a gravitational wave detector that will be launched in 2030 called LISA that will look for different kinds of sources, supermassive black holes. You can use pulsar timing, and I'm not going to talk about that too much, but basically you can, using radio astronomy, you can also detect a different kind of gravitational waves. And perhaps the most exciting thing, if we could do it, is the Big Bang itself produced gravitational waves. And unlike light, which you can't detect from the Big Bang because of the nature of the way the universe evolved, you can only see the birth of the universe by looking in gravitational waves. So there are a number of experiments that hopefully in the next 5 to 10 years we'll be able to sense the residue, the gravitational wave residue from the birth of the universe itself. And I think that's just very, very exciting. So I'm going to stop here by acknowledging the 1,000 people that made meaningful contributions, my colleagues in LIGO and also in Virgo. And I want to say, finally, that we just turned on November 30th, so we're back running again. So I think it'll be very exciting, so I ask you all to stay tuned. Thank you.
Thank you very much, David. We're going to give you a moment to catch your breath, have a drink. We're going to take some questions now. So if you've got a question about gravity waves or indeed other areas of cosmology and physics, I'm sure that they would be happy to have a crack at those. Just want to say again thank you to the University of Queensland for putting tonight's event on, and also to the Edge for hosting us. Edge hosts a lot of other great events here related to science and technology and manufacturing, so check them out. If you have a question, wave it around and we're going to come around and collect them now. Also, BrisScience will be back next year. This is the last event for 2016, but we'll be back in January, February. We're still confirming next year. So hop on the mailing list or Facebook, and we'll look forward to emailing you very soon about next year's talks. All right, I'm just going to open up Twitter here. Thank you. Okay, so questions. All right, so first question, pretty broad, but
okay.
if you're game, why do gravity waves, neutrinos, and photons all travel at the same speed, if indeed they do?
So, why do gravity waves?
Gravity waves, photons, and neutrinos.
Okay, so gravitational waves and photons travel at the same speed, the speed of light, because they're massless. I mean, it comes out of the theory, but basically they possess zero mass. All right, I didn't use this word, but I will use it now. The quanta of gravity is called a graviton, like the quanta of light is called a photon. All right. In the theory, they don't have any mass. In fact, our experiment, LIGO, was able to the limits that we could measure it, show that the mass of the graviton was basically zero. Not quite, but we put a limit on it. Neutrinos are slightly different. Neutrinos do have a little bit of mass, and so therefore they don't quite travel at the speed of light. They travel at, I don't know, 0.999996 times the speed of light. I don't know exactly. All right. So the reason has to do with mass. Massive objects cannot travel at the speed of light. Massless objects, like light and gravity, have to travel at the speed of light.
Great. Okay, next question. How significant is the damping effect of gravitational waves, or does it even exist, and what influences this damping?
Great question. So the question basically means, do gravitational waves attenuate because they get absorbed or something happens to them to weaken them as they propagate? The answer is that as they propagate away from the source, these two black holes, the amplitude of the wave falls off as 1 over the distance, all right? But that's just natural physical propagation, all right? There's no absorption there. The reason, again, that this experiment is so hard is because they don't really interact with anything. So the answer to the question is, in general relativity, we do not believe that these gravitational waves are damped. In fact, the ones that came through our detector in September of last year, they're still propagating away. They're still going off further and further away. Having said that, there are theories that are starting to look at the coupling of gravitational waves to matter. And there may be a way that they could couple to neutrinos or to WIMPs, dark matter, for example. Having said that, the theories, I would say, are speculative at this point, and until they get more firm, we don't believe that gravitational waves are damped.
Okay, question that may be a little bit related. How could you tell it was 1.3 billion years ago? How could you distinguish between that and a smaller, closer collision?
Yeah, so I was a little bit disingenuous, all right? It was 1.3 billion years ago, give or take. So the error bars on that measurement are actually measured in hundreds of millions of light years. So it could have come in at 900 million light years. It could have come in at 1.7 billion light years. How do we get that information? Basically, it's all encoded in that wave, those two waves that I showed you, the red wave and the blue wave. All right, and I'll just walk through the algorithm very quickly. The first part of the waveform, the one where the frequency is increasing or the crests are getting closer together, that tells you something about the masses of the wave. All right, where the wave ends, at what frequency it cuts off, tells you something about the masses of the black holes. Where the wave cuts off tells you something about the final mass of the black holes. So the information about the masses is there. Once you have the masses, all right, you can then say, where do these waves come from? And we get that from the time separation, that there was a little bit of a time offset. So you now know where they came from in the sky. The next thing you know is once you have the masses, you also know naturally, you can calculate what the natural radiation amount of radiated energy is close to the black hole. And then you compare that to what you actually measure in our detectors, and that gives you the distance. So that's roughly how we know.
So I'm going to ask my question,
okay,
which is, so your first detection happened very soon after you first switched on.
We weren't even running, actually. That's the even thing. We were in an engineering run at the time, yeah. Mm-hmm.
So what was the response of people there? Did you think it was a prank, or fake data was injected to test you, or did you really believe it was happening?
So that's a very insightful question. And the reason it's a very insightful question is because of something that we had decided to do naturally. So we're a tricky bunch of people in our collaboration, and we trick each other all the time. And one of the ways we trick each other is we inject fake signals into our detector, and we don't tell people. We tell them that there might be a fake signal. We call them a blind injection. So there are 4 people out of that 1,000 people that inject fake signals in, all right, and don't tell anybody, and then the rest of the collaboration has to go find the signal. This is the way we train ourselves to look for these kinds of events. So there was a lot of people in our collaboration that said, oh, this just must be a blind injection. It's a fake signal. We're just being tested. There's no way that they just turn on that we could see.
It's too good.
How lucky is that? Yeah, can't happen. I was one of the 4 people that knew that we didn't do a blind injection. So my reaction was, wow. I will tell you that a lot of people, even a month or 2 into this, were still calling me up or sending me emails saying, Dave, stop pulling our leg. This really is a blind injection. Don't make us waste our time on this. And I said, no, it isn't. Let me tell you the other side of that coin, though. The other side of that coin is that we ourselves were so concerned about this signal, it was too good, that we said, maybe somebody snuck that signal in there. We call it the evil genius scenario, or maybe the Chinese hacker scenario, where somebody comes into our detector, figures out the right files to overwrite, and can sort of in software inject a signal. We checked it out, and it turned out it wasn't. So I would say pretty soon after the detection, I was convinced. It took a while for some of the other people to be convinced.
Who had to make the final decision that, yep, this is real, we're going to publish?
The whole collaboration. All right, so this paper has 1,000 authors on it, and I can tell you, writing a paper that has 1,000 authors is no easy thing to do. In the end, we did something very clever, and I credit the spokesperson for the collaboration. Her name is Gabriela Gonzalez for this. We had the paper written. It went through 14 revisions, all right, and I mean every word was picked at. And in the end, we didn't vote on whether it was real. We voted on whether to submit the paper or not. And the votes were overwhelming. I think 98, 99% said submit the paper, and so that was it.
Good. All right, unfortunately, we're almost out of time. One comment from somebody who notes that your political cartoon, your first one, was from First Dog on the Moon, an Australian cartoonist.
Oh, is that right?
Is the name of the cartoon.
I know that now, thank you.
Making your comment about being over the moon wonderfully puntastic. So they were very happy with that moment. The final question to ask you was, and you can go for just one, but what are the 3 big questions you would like to answer in the future about gravitational waves?
Okay, I'll start with the top. The big one is, what did the universe look like at the beginning of the universe, the Big Bang? And you can only get that from gravitational waves. And that's something that may happen in the next 5 to 10 years. Number 2, all right, there's a theory, astronomers will tell you that these binary neutron stars that I showed you, these sort of picture artist conception of, produce bright, very hard gamma rays that are detected by satellites. They're called short, hard gamma ray bursts. All right, these neutron star collisions are actually quite interesting because nuclear physicists and astrophysicists believe that this is really the only way to produce certain classes of heavy elements. So gold, for example, cannot be produced by stellar processes, by a supernova or just stellar burning of nuclear material. All right, you have to have something more energetic, and the energetic thing is neutron star collision. So the bling that you all wear, all right, was probably produced in a neutron star. Question is, until you see a gravitational wave together with those gamma ray bursts, you don't know that. All right, so what we really want to capture is a neutron star merging with another neutron star with a gravitational wave, and then seeing the gamma rays that come very soon after. Number 2. Number 3, and this would be the holy grail, the home run. All right, Einstein's theory of general relativity is a theory that has stood the test of time for 100 years. It can't be the end, because we know there's another theory called quantum mechanics, which very well explains the subatomic world, right? And theoretical physicists have been trying for almost as long as there have been quantum mechanics and general relativity to bring those two things together. The latest attempt is something called string theory. They've been working on it for a long time. It shows some potential and promise. It's a very complicated theory. We now have a way to test general relativity in a completely new regime where we're looking at strong fields. I mean, the fields around black holes are incredibly strong, the warping of space-time. So we might see something in our data, and it would be encoded in those waveforms, that tells us that general relativity is not correct, or it gives us the hint for where the next theory comes from. So that would be fantastic. And I actually have a 4th one, but we don't have to talk about it.
Well, it might be a chance there's a conversation open before we go out for food and drinks in a moment. Ladies and gentlemen, could you please join me in thanking David Reitze for a fantastic talk.
Thank you. Oh, I did. Wow. Thanks.